So, good afternoon, Anna, and
Good
we are live
afternoon,
again.
Francis. Nice to see you again.
Nice to see you again after yesterday, and probably I will see you also tomorrow.
Yes, that's true.
So, welcome to another, I would say, interesting lecture by Anna on sensors. And since sensors are the heart of this course, where everybody will work with at least one sensors, so knowing them about a bit more would be helpful, we believe. So, Anna, the floor is yours, and I will, as usual, help you with the questions from Discord, and probably we will have a great session.
Thank you. Very nice. So let's start. So, what is it about today? I would like to talk to you about sensors. However, I'm also not really a sensor electronical engineer, so I cannot really tell you how to build a new sensor or how to develop a completely novel one. I can also very little tell you about how they internally work. What is very important for us as IoT people is actually to understand what are the types of sensors and which practical properties about them you need to know so that you can select the proper sensor for your work and you know also how to handle some common errors. So let's go. First of all, what are sensors? Sensors are nowadays really everywhere. So here, for example, in this slide, you see three examples. One is this touch sensor, which we're using here in Germany to touch that you would like to go on a traffic light, and so that the traffic light becomes green. So it is a kind of a touch sensor at the end. Then, of course, you know your smartphones. They're also full of all possible sensors. Accelerometer is there, and there is a camera, which is at the end a very popular sensor. There is a GPS, which is also a sensor, and so on and so forth. And of course, these smartwatches, they're also packed with different sensors. So it is a physical device which is typically very small, but it can be also very, very complex. So you can compare, for example, from a temperature sensor, which is typically tiny and very, very cheap. You can go up to a night vision or infrared camera, which is a really complex and expensive sensor at the end, to and all of them at the end are trying to sense some environmental phenomena and to turn it into into an analog or into a digital signal at the end in order to be used in something. So for us, it's really important that we are not only using the sensors in order, for example, to see what the temperature outside is, just to check whether I need a jacket or not, but it's actually transferred at some point to a digital signal which we can analyze and we can use in an IoT device or in an IoT application. So there are many different classifications and types of sensors. I really can only scratch on the surface here a little bit and tell you about some which are very popular. So for example, many of them are based on the so-called resistive properties, properties, or capacitive one. Resistive means pretty much that you have that the sensor, the device itself experiences some change in its resistance depending on the phenomena it is measuring. For example, a simple temperature sensor is very often a resistive one because depending on the temperature, some piece of this device will change its resistance, which you can potentially then measure and use this difference, then transfer this difference into the signal, which tells you at the end what is the temperature. It's exactly the same way of when you are measuring the change in inductance or the change in capacitance. It doesn't really, well, of course, it matters a lot what you're measuring and what you need, but at the end, the principle is the same. The environmental phenomena which you're measuring is changing a property of your device, of your sensor, and that change can be measured and can be translated into the real measurement as we understand it, for example, in temperature for in degree Celsius or in or any other metric. Others which are very popular, which are not, let's say, based on power and electricity, are, for example, elastic ones, where you would like elasticity will change, or thermal ones, or photoresistive ones, or piezoelectric. Piezoelectric is, for example, the one which generates an electric signal by changing the pressure. So this is, for example, what you can find in touch buttons, or you can find it in sensors for shoes, where the fact that you are pushing on this sensor actually creates an electric signal, and the strength of this electric signal now can be measured, as opposed to the resistive, inductive, and capacitive, where the whole chain is actually changed. Elastic, thermal, and photoresistive, they work pretty much in the same principle. Photoresistive is when light is changing and creating electric signal. You can measure this electric signal. The same is for thermal and for elastic. So as you can see, there are many ways the sensors can work. It is not necessarily that you actually know how your sensor is working. What is much more important is to understand that you have to read the specifications very exactly. So, what is normal, for example, is that a particular sensor will be working well in kind of room temperatures with some sort of humidity of the air, that it will have also some sort of a spectrum. So it will, for example, the temperature sensor will give you good information between minus 20 and 20 degrees, for example, but you should not count on it whenever it starts getting really hot, or it starts getting really cold. So it's important really to understand that those specifications have to be followed, because otherwise your whole IoT system and your whole IoT device will be misperforming, because simply you have wrong sensor readings, because you misunderstood how the sensor is working. Another way of classifying sensors is to say, well, are they actually active or passive? Active means that the sensor actually has to actively start a measurement. So, for example, in an infrared sensor, which is trying to understand whether something like an obstacle is somewhere in front of you, it actually has first to send the signal out, so an infrared signal, and to see whether it gets reflected. And only with this reflected signal, it can measure whether there was an obstacle, where is the obstacle, and so on. So this is called an active sensor, which means that it actually it needs more energy, of course, and it needs to actively do something to start the measurement and to end the measurement. There is also the possibility, of course, to have passive sensors, which are kind of always on, right? Like you're constantly, like, for example, here in this small picture, you see that the sensor is waiting for somebody else to reflect, to send an infrared signal. Okay, so this is what happens, for example, when you push the buttons on your TV remote control, is that the passive sensor on the TV will receive that one, but yours is actually an active one because you are pushing the button. So this differentiation is important, especially when you are implementing that later. Some people have some sort of a small misunderstanding here when they use sensors in software implementations, that they expect the sensor to return a value immediately. So they kind of expect to have some sort of a function call, right? Like you say, temperature sensor get value, something like that. And that works well if it is a passive sensor, which can really read it straight away and return immediately the value. But that doesn't work if you have an active one. It either will block the system, which you definitely don't want to, because in IoT, you know that we typically have only a single process system, which means that if you block your process by waiting for a measurement to come back, then you block the complete system and bad things can happen. For example, you can miss packets, you can miss interrupts, and so on. So with active sensors, you actually have the so-called split event, which means that you start the measurement, and whenever the measurement is available, then you get a software interrupt back in order to understand that, okay, I have my measurement back. So this differentiation here is very important for us, because it creates a lot of implementation problems. So another way, of course, of differentiating, which is also very important in IoT, is whether we actually have an analog sensor or a digital sensor on hand. With a digital sensor, it's really nice because what you get actually on the let's say on the hardware pin where you have connected your sensor is a purely digital signal. So you can decode it immediately as a digital one, and you don't need anything else, and it's already there. If you receive an analog signal, which means this, like let's say the voltage here is changing this way, you cannot transfer that immediately to a digital signal. You have to use an analog to digital converter. And typically in many platforms, you need also to use particular pins on your hardware where to connect to. So it's typical that IoT platforms will have special pins which are ready to go for digital inputs, which are simpler. And you will have only few pins which are connected to an analog digital converter, and vice versa, where you can actually use analog sensors or even actuators. So this is not straightforward, and you have to be careful where you connect it exactly. Do we have any questions so far?
I received one, but I was not clear about the question, so I
Okay,
asked back. So
yeah,
it's,
let's see what happens. But go ahead and ask questions if something is unclear or you would like more information about something.
so
So,
it,
yeah.
it was about like you talked about problem, uh, something that interrupts. I don't recall what it is about. So that was something about a problem, but probably
You mean when I was talking about software interrupts?
yes.
Oh, okay, maybe too many keywords at once. Do we actually have a lecture on properly on the hardware design of IoT?
Not really.
Not really. Maybe we should introduce that for next year. So, okay, everybody knows that an IoT device is a very small and simple device, right? And so we have various components which are connected to the microcontroller. And the microcontroller is kind of the brain of the whole system, right? But it's relatively simple. So it has these pins. Pins means a connection to the outside world where you can connect, for example, to a particular sensor, to a particular actuator. Some of them are connected actually to your battery. Some others are connected, for example, to a real-time clock. So all components which you would like to connect to your microcontroller, they're connected via pins. Those are these small legs coming out of the microcontroller, right? And so whenever one of these components would like to send you something and to say, hey, I have something, let's say the real-time clock would like to give you the next tick that it's now time has passed, then on this pin, a signal is coming in, and this is called an interrupt. And interrupt means that the normal processing of the program on the microcontroller is interrupted because something came from outside and has to be taken care of immediately. A hardware interrupt means that this interrupt is coming from one of the hardware components, but it can come also from a software component. For example, when I was trying to give you this explanation of this split event and the active sensors, so what happens here is that I cannot simply read the sensor value immediately because the measurement has to be started and then measured and so on. So what I instead of that do is that I say start the measurement, right? And then I leave it to do it. Okay, so the sensor by itself, it is not part of the microcontroller. It's an individual component. That is taking care now of starting the sensor, taking the measurement, and whenever it's ready, it can now signal back to the microcontroller, I'm ready. And this is called a software interrupt because it's now coming from a software piece and not necessarily from a hardware piece. But all of them are actually managed in the same way. So I have some sort of a program which looks like a loop, right? And whenever something interesting is happening, I can interrupt the main program and say, hey, something came on the sensor. Hey, you have a new tick from the real-time clock. And these events are called interrupts. And so that's why this is quite important to understand, because the microcontroller really has a single process only. We have only one CPU if you want, right? And so I can do only one thing at a time. Okay, I don't have a multi-core CPU like what I would have it in a proper desktop computer, in a laptop, or in a smartphone, but I only have one process, and so everything has to fit somehow in between.
Yeah,
Okay.
good to know. Yes, and since you're talking about also about microcontroller, so there was a question about that. So, is there any specific pins in microcontrollers that analog signals applies to, or
Yes, typically yes. Like it depends. It's not. Sometimes it depends on the microcontroller. Sometimes it's part of the embedded device itself. We had this discussion yesterday. There was a very nice question: what is embedded device? Embedded means that you put all of these small, tiny hardware components on one platform, and you don't touch it anymore, right? Like it's one thing. And so sometimes the microcontroller has some requirements on which pins have to be connected to digital inputs and to analog pins, or to analog inputs. Typically, however, this is a designer decision of the platform itself. So I don't remember by heart what were the PICOMs, and especially the low PIs or the phi PIs. But in most of the platforms, really, you have a specification by pin, which ones you can use for analog inputs, which ones you have to use for digital inputs. So in Arduino, for example, pins 1, 0, and 1 are reserved for analog. Everything, some are reserved, can be used analog and digital, and some are reserved for digital only. So you have to check on those particularly for your platform in order to know where you're allowed actually to connect this or that thing.
yeah, I guess also for PyCom they have some dedicated pins for analog and digital signals.
I'm pretty sure about that. I just don't remember the numbers.
Yeah, and since
Exactly.
we're also talking about microcontrollers, there was a question about uh, asynchronicity. So, can you program asynchronously in these microcontrollers or ESP32s?
We wanted to talk about sensors and not about embedded programming. Okay, so yes and no. You can, with MicroPython, you can have some sort of a asynchronous programming. You have to be very careful because you're actually not implementing with individual processes, but you're implementing with individual with non-isolated processes, let's say. So if you need to you need to synchronize them, and you need to do it manually. So you cannot simply say, oh, I fork this process as you would do it in any other system probably, and say, oh, they're synchronized and they're isolated. So no memory leaks, nothing like that. This is not true here. You easily get leaky memory here. You start writing at the same memory, it's really bad. So please be careful when you use that. It's very typical that you use it, but you need to use the so-called atomic operations in order to isolate pieces of your code which are writing or reading important data. Okay. 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 So I would say we continue a little bit with sensors, and then we see where we end up to it. So what kind of parameters do exist on sensors? First of all, as I was saying, and these are things which you can check on your specification sheet of each and any sensor. You cannot rely on having something which you just wish to. You have to check it specifically for that sensor. So the first one, very important, is the range. So what kind of values I can expect? What are the minimum and the maximum values I can expect? For example, for temperature, I can expect everything from -50 to +80, okay, or from 0 to 100. It's very important to know that, because Otherwise, you might get data which is not useful to you, or you might have a range which doesn't fit your application. So for example, if you take normal temperature sensors and you put them on a rocket engine, they will burn immediately because their range is just not specified, right? Like that will not work out. There is also the so-called resolution. So how exact and precise is actually the value? Are we talking here about 0 point something or about 0.00 something, right? This is very important for some applications. Sometimes you don't really need to know it because you're happy with anything. For example, if you have, let's say, water content in the soil, for agricultural applications, it's more or less enough to not even have a comma there, but you still need to understand what is your resolution. There is also so-called error, so you can pretty much be sure that your sensor is not perfect. There will always be an error. So you can try it out also yourself by simply measuring several times at almost at the same time. So for example, instead of just measuring once the temperature, you take 10 measurements one after another. And then you will see that there are some errors. So it's obviously that the temperature didn't change so fast, but the sensor itself has some error range, and you need to understand what it is in order to design again your application accordingly. So for example, here I have, let's say, an actual value is 15 volt, but then what I measure is 14.8, and the error plus minus 0.5 is allowed. So it is okay, right? Like this is something which I can live with. But if I'm into very precise things, let's say for medical applications, I will be very careful about the error. You know, probably also one sensor which has a very big error and sometimes very nasty, GPS. It's also a sensor, and the error is very typical to be 5 to 15 meters, which is of course not optimal. And it looks like you're in the middle of the lake, but you're actually on the street just next to it. So this is kind of a typical problem there. There is also something which not everybody is aware of. This is the so-called linearity. Linearity means that there is a mathematical linear relationship between the different measurements. So if you, for example, the error, I think I can explain it. So for example, in the error, let's say for lower, if the error is the same for lower temperature and higher temperature, then obviously it's kind of a linear relationship, right? So I expect this small error at these temperatures and pretty much the same properties also for higher temperatures. This is unfortunately not always true. So it can happen that you get a non-linear sensor which increases its error or its precision or its resolution depending on some environmental properties, which are typically humidity and temperature. And or direct sunlight, which at the end is temperature, is, for example, a problematic issue with sensors always.
And I guess there is also a relationship between resolution and sensitivity, right? Like
Yeah,
if
yeah,
if we,
exactly.
if we mean by sensitivity is that a slight or very small change in the environment should be detectable by the sensors. So
Yeah, exactly. That will be the resolution at the end, right? The sensitivity or resolution is all the same. This is how sensitive your sensor is. This is absolutely correct. And the most important overall message here is that don't ever expect perfect values.
yeah, there was a question on Discord. Yeah,
Exactly. You can always expect problems with the values themselves. We will get into more precisely about that in the next slides. But pretty much expect problems, expect that different measurements will give you different results, even if the environment did not change at all. And you have to cope with those because there is no perfect sensor, simply like that doesn't exist. Okay. So precision and accuracy is a very important, let's say, topic because many people confuse what is precision, what is accuracy, and some believe it's actually all the same, but it's actually not. Here you have the definitions of the accuracy and precision. So accuracy refers to how close a measurement is to the true or accepted value. With other words, if my GPS location is just 1 meter away from I'm really ER, then the accuracy is very high. Precision, however, is how close individual measurements, many different individual measurements, will be to each other. So, with other words, if I measure my position with a GPS many different times, and it is always around 10 meters apart from me in one direction, then the precision is actually pretty good, but the accuracy is bad. So these examples are also provided here in these graphs. So in the first graph, here is the sensor reading with annotated by this small x. And the actual value, let's say your position, is this one, the big cross. And so if the accuracy is low and the precision is low, then there is a kind of a cloud around the actual value. So they're not precise and they're not accurate. Sometimes they're a little bit closer than some other times, but they're kind of a cloud here around you. If the accuracy is low but the precision is high, it means that the measurements are pretty far away from your actual position or your actual value, but they're all together in a one very compact cloud this time, right? So they're all kind of saying, no, I think I'm 10 meters, so just west of where your real position is. So it is again, of course, an error and it's not something good, but on the other side, it's maybe a little bit easier to explain and to understand and to cope with it when the values are at least in one compact place. And then it can be also exactly the opposite, to have high accuracy but very low precision. So the cloud now is more compact. So the individual measurements are closer to the actual one, but they're kind of different. They're jumpy around it. They're not on one side or always have a skew towards west or towards something else, but they're actually very jumpy and you still don't know where you're exactly. But you can build an average, which is, for example, a very nice property here. And then the optimal, what you would like to have, is of course to have high accuracy and high precision at the same time, which means that here the measurements are very close to the actual value and they're all in a very small compact cloud here. Okay, so that is the difference between precision and accuracy, and it's an important property. Another problem with sensors is their own energy supply. So sensors, even passive ones, they need power. Otherwise, they don't work. And otherwise, we cannot get a digital or analog signal out of them. Like that simply doesn't work. So the problem is, however, is that each individual sensor has some sort of a nominal input voltage. So in the specification sheet, you will see things like this sensor needs 3.3 volt, or this sensor needs 5 volt, or it needs 12 volts. And if you supply it correctly, all is good and they're correctly functioning. Now we're getting into embedded systems back and into those problems. And very often in embedded devices, you will not have the so-called voltage regulator. A voltage regulator is a hardware piece on the embedded device, which makes sure that either the voltage is above or approximately at one particular level, let's say 3.3 volt or 5 volt typically for embedded devices, or that if it drops below that, it shuts down the complete circuit, which is very important because most of the components on board, they will continue working also with lower voltages. And that goes for quite a long time. Like they will not simply switch off at some point, but they actually continue trying and trying and trying. And some very weird side effects arise. Let me show you one, which is connected to sensors. But this is not only limited to sensors. So here we did an experiment some time ago. together with a colleague from Berlin, Thomas Menzel, we did the following. We took a temperature sensor and we connected it to an adjustable voltage input. And we started changing very slowly and very systematically how much input voltage you have. And you see the following. The temperature was in the room was completely stable. So the whole experiment took something like 5 to 10 minutes. So the temperature was kept stable. And what do we see now here? Interestingly, like the nominal voltage, input voltage of the temperature sensor was 2.2, exactly here, the beginning of the x-axis. And those specifications are available in the specification sheet of the sensor. Now we started going down with the battery voltage. You see that the numbers here are going down, okay? And so for some time, 2.15, 2.1 volt, 2.05 volt, the temperature sensor was giving correct results. It continuously told us that it's 25 degrees. Okay. And then suddenly it starts looking like it gets a fire, right? I mean, the temperature starts increasing dramatically until it hits simply the maximum, the range. You see here also the maximum range of this sensor. It cannot give you a higher value. Whatever it believes it is, it just cannot give you that. So what is happening here? What is the explanation? The explanation is that because it's a resistive sensor, so the temperature changes the resistance of the sensor, and that can be measured. However, it needs a point of comparison. And the point of comparison is the input voltage. And whenever you change, sorry. So whenever, like you're comparing something to, let's say, this, right? And you start comparing and you say, oh, it's 10 more, oh, it's 20 more, or it's 10 minus. Then you can calculate what your temperature is because you know somehow that, okay, this is my nominal temperature if I want. But what will happen if you start pushing on the comparative value? That starts dropping. And now suddenly, of course, your value, your sensor value looks like it's increasing. So this is something which you can see sometimes with some platforms, not all of them. Like if they have voltage regulators, you can check also on that. Then you can be sure that you don't get at least those effects. But if they don't have voltage regulators, which is very often the case, for example, most Arduino platforms don't have them, then with dying batteries or bad, lower batteries, like low quality batteries, you can expect to see such very weird side effects. And that will be propagating not only into the sensors, but also into your memory, external memory. It will be propagating into your actuators and so on. So all components are affected by this side effect. Okay. Any questions about that? Because this is quite complex.
Yeah, not really about this, but there was about accuracy and precision, some discussions going on Discord.
Okay.
So some people were looking for real life examples of accuracy and precision, but others already answered on the Discord. So
I think GPS is the best example. Right? Like try to imagine that with a GPS sensor. It's the easiest way of understanding that.
yeah.
Okay. So that's about sensors and input voltage. This is important to understand that this input voltage is not only just to run the sensor, but it's typically used also as a comparative value, like not necessarily directly the voltage, but the voltage is part of the equation. So whenever you change one of these reference points, you completely change the output of the sensor, and this is nasty. Another very important topic, let's say, is the so-called sensor calibration. It's connected also to accuracy, to precision, and so on and so forth, and to those reference values which we're using to calculate the real sensor value which we would like to have. What is sensor calibration? if you take a sensor, which is a special an analog or a digital sensor, at the very beginning, it is a little bit like a thermometer without a number, right? Like it's like taking a thermometer and not knowing what these uh, in the individual lines there actually mean. Like, where is the zero? Is it on the top? Is it in the middle? Or is it down there? So calibration puts back those numbers into your sensors so that you can actually understand which measurement, which electric measurement of the sensor corresponds to what sensor value which you can read. For example, what voltage corresponds to which temperature in degree Celsius. And this is called sensor calibration. And there are typically two main methods to do that. You can use the so-called reference sensor. So what you have is that you have a digital or an analog sensor, and you have a reference sensor which already has its numbers and knows exactly what is the temperature, the surrounding temperature. So for example, you can take even a very simple analog sensor like the ones so you use on the your window, right? And then you put both of these sensors, like the one which you like to calibrate and the reference sensor, you put them in a zone with equal temperature or equal phenomenon. Okay, it can be also salinity, it can be also air quality, it can be anything. It's important that they're in a zone which has equal phenomenon which you would like to measure. And then, of course, you can measure the difference. Like you can see the difference. You can see, okay, at the temperature 25 degrees, I measure this electric signal. When I change it to 10 degrees, then I measure that electric signal. Okay, something else. And now comes also this linearity into the whole story back. Because if it's a linear function, you only need two measurements. You can measure at 10 degrees, you can measure at 25 degrees, and you draw a line in between. Unfortunately, not always things are so easy, so you need to make more measurements and then fit a more complex function over that. This is typically something which the manufacturers already did for you, and you just have to make one single measurement and to push the line up or down. Okay, so the line itself, even if it's a complex curved line, is already defined for you by the manufacturers. And you only have to recalibrate your sensor in terms of only one point, which pushes it up and down. But this is also part of the specification of the sensor of how to calibrate it. The other possibility to calibrate is the so-called reference environment. So instead of using a reference sensor in an unknown environment, which you can simply measure and change a little bit, you actually define a zone with a very well specified phenomenon. So for example, you put it in water, which has a very particular temperature already by itself. Like, of course, you have to check it with something, which again will be some sort of a reference sensor, but you can do it also this way around. And then you can do exactly the same. Like you simply know that now it should be measuring 10 degrees. Now it should be measuring 25 degrees. And again, the same story starts, whether it's linear or non-linear, how many measurements you need in order to get your calibration line. This is very important because you will notice very often especially with a little bit more complex sensors like volumetric water content is such a sensor, or salinity sensor for water is such a one, or pH sensor for soil or for water. They need to be carefully calibrated and regularly recalibrated. All is specified by the manufacturer in the specification sheet, but you need to know that it exists and that you need to take care about that. That's it actually from my side for today. I hope it was a nice short overview of what kind of nasty problems are waiting for you when you use sensors, and that you're now a little bit better aware of how you can help and how to navigate in this area.
Mhm. Yeah, thank you for the nice presentations, as always. So
You're
there was, I think, a couple of questions that I did not pick up during your talk. So maybe we can go through them and
okay. Let's
wrap
go.
up the session. Yeah, because the students also have workshops in 20 minutes, so they want a break in between.
Sure.
So the first one was how will voltage spikes and drops to different degrees affect the ESP32 and the sensors that is powered by it?
I didn't get that. Sorry. What kind of
So
spikes?
probably the voltage spikes. So the up and down of the voltage might have some performance effect on the ESP32, right? Or maybe.
Well, it depends on what kind of voltage you mean. Like if it is the one from the sensor, which
Mhm,
is connected on the pin, this is simply the value which it delivers. That's not a problem at all. Like this is specified to be like that and to be changeable. It's not a supply voltage.
mhm.
It's an electric signal to read out and to transform into a sensor value. If you're talking about the input voltage of the ESP,
Yeah, I guess there is the input voltage. It's
okay, then well, the spikes, typically there are no spikes up because no battery can really do more voltage than its nominal one. Typically it's less. And we if it goes way below one of the components can manage, that component will switch off.
mhm,
So if it is, and the problem really is that different components have different requirements. So for example, the external memory is the one to say goodbye the first, because it's need a very specific input voltage. The microcontroller, the ESP32, is actually the last. That has the biggest resilience of all of them, like typical.
yeah,
And some sensors, they also might simply switch off or deliver wrong results, as we saw before.
yeah. And another question also about sensors. So if you connect the sensor on the 5-volt connection on the board, will poor battery still affect the measurement? Let's
It
say.
depends on how much the sensor requires.
Mhm,
And it can burn actually if you put it on more.
okay, yeah.
So in general, you have to be careful. Like each component has its specifications. What is the input voltage? What is a tolerable input range? And you have to consider those. If you don't, there is always a risk that either your system will underperform, so for example, switch off or deliver wrong results, or do some only half of the things you wanted it to do. For example, the external memory might write some of the data, might not. Um, and on the other side, if you give it too much input voltage, you might burn your system completely.
Yeah, and I guess to this point there was a related question right now. So, can someone recalibrate a sensor to work on different voltages? Mm,
No, the calibration has nothing to do with the input voltage of the sensor.
mhm,
This is only how to interpret the values which are coming out of the sensor, because the real values, the raw values from the sensor, are
okay.
actually an electric signal. So it's either voltage or resistance and things like that. And
So
those have to
it's
be
output
simply
basically.
interpreted. And the calibration is for reinterpretation, not for changing the input voltage.
Okay, so basically it's the output that you're talking about, not the
Yeah.
input voltage. Yeah, yeah. I think that's all we had from Discord. But
Okay.
thank you again, Anna, for your informative talk. And probably we will see also tomorrow on more or energy. I see there are more interest in the energy
I
from the.
see there is a lot of interest in energy. Yes.
So we will learn more about, I guess, energy on IoT tomorrow at 6.
That's right. So see you tomorrow. Thank you very much.
Thank you very much, and thank you everyone for joining us today.